Hello, my name is Zuzana Marcalikova. I am from the Czech Republic. I am PhD student and study on Technical University of Ostrava. My research area is fiber reinforced concrete for advantage design concrete structures. I have prepared a paper for this conference with name Approach to Numerical Modeling of Fiber Reinforced Concrete. Fiber reinforced concrete have many applications for structural design of building systems. Fiber reinforced concrete have many variants. They differ in the basic matrix concrete and type of the fibers. For example, shape, material steel or polypropylene length. For the analysis of fiber reinforced concrete elements, it is necessary to use numerical method, which can include advanced computer simulation of real behavior. However, the limitation of numerical modeling include the necessary knowledge of detailed mechanical properties. The choice of fiber is determined according to the purpose of use of fiber reinforced concrete. Great attention is paid to the determination of mechanical properties, their testing and identification of mechanical parameters. The goal of the paper is presentation of using differently the approaches to numerical modeling of fiber reinforced concrete for 3-point bending test of a beam. The basic tested properties of fiber reinforced concrete include usually determination of compressive strength, tensile strength, splitting tensile strength, bending tensile strength, and density determination. Particular attention is paid to the tensile strength testing. The frequently used splitting tensile test is technically simple compared to the bending tensile test. However, in the case of simplified designs and analysis of fiber reinforced concrete, the expression of tensile properties in the form of equivalent tensile strength is most often preferred. In the case of computer simulation, it is preferable to determine the fracture energy and a suitable idealized softening diagram. For testing of fiber reinforced concrete exist a number of recommendations, standards or design code. However, the resulting mechanical properties are also influenced by the test configuration, for example, 3-point or 4-point, and sample dimensions. When interpreting the test results, it is also necessary to take into account that the character of tensile properties is expressed for basic types of stress: tension, pressure, shear, or torsion. For mathematical models of material. For numerical modeling and analysis, the finite element method and nonlinear analysis are often used. Numerical method is used where for mathematical model of material is chosen fracture plastic model and 3-dimensional models. Research and paper include experiments in the laboratory and numerical modeling. For experiment chosen 2 series of samples with different in the type of fibers used. Dramix with hooked ends fibers in figure A for the first series and Dramix small fibers in figure B for the second series. Test series have some dosing. Test series have also the same basic concrete matrix. The parameters of the concrete matrix shown in the table. The concrete matrix includes cement, water, fine aggregate, coarse aggregate, and plasticizer. Laboratory tests include compressive strength for cube, figure A, splitting tensile strength for cube, figure B, and bending tensile strength, figure C. Beams for bending test have each a 50 mm notch. The resulting mechanical properties are shown in table. The evolution of the 3-point bending test include also determination of load displacement diagrams. LD diagrams were used for numerical modeling. For the numerical modeling, it is possible to use finite element methods and nonlinear analysis within the Athena computational systems. The created three-dimensional numerical model simulation the 3-point bending test and used the fracture plastic material model. Was used 8-node isoparametric finite elements. The fibers were taken into account in the concrete by two concepts. For dynamic small fibers, series 2, figure B, was used typical concrete tensile softening, figure A. However, tensile strength and fracture energy were modified. This is possible designation in this case modeling as effective tensile strength and fracture energy. For the model case, it was effective tensile strength 0.95 and fracture energy 900. In the case of dynamics with hooked ends fibers, series 1, a concept combining and smart reinforced model and plain concrete model was chosen to illustrate. For the modeled case, it was concrete with input parameters. Compressive strength for cubic 24, compressive strength for cylindrical 20, modulus of elasticity 80.5, basic tensile strength 1.5. For fibers was input parameters, yield strength 1000, tensile strength 1050 and residual strength 100. The figures show a comparison of results from laboratory tests and numerical modeling. The left figure shows results for hooked fibers and right figure shows results for small fibers. The results of the LG diagram from numerical modeling are with the experiments very similarly. Conclusion. The paper deals with the approaches to numerical modeling of fiber reinforced concrete for 3-point bending test of a beam. The test sample used different the type of fibers. Dynamics with hooked ends fibers and dynamics small fibers were used. The concrete recipe was the same for both types of fibers. Tensile softening character of the 3-point test was different for both types. For test reasons, two concepts were chosen for numerical modeling. For the case of 3-dimensional fibers, it is possible to use a concept combining a model of smart reinforced model and modeling of plain concrete. In the case of small fibers, it is possible to use a model for exponential softening for plain concrete, where the input parameters are modified to the effective volume. This numerical modeling access made it possible to get closer to the resulting the LG diagrams from laboratory tests very well. However, it is difficult to choose optimized the methodology for determination of material properties. The authors will focus on this area in future research. Thank you for attention.